All right, well, welcome to actual class. Sorry about the technical difficulties. Hopefully we can resolve those. I think it must be something to do, though, that's out of our control, because it seems that some computers work and some don't. You'll notice that some computers, at least down here, including my own, give you an error message when you start up ArcGIS right now. It looks like that's because of our annual license is about to expire. We'll get that problem solved both here and in Hattiesburg. All right. So today we're going to continue our discussion of basic raster calculator operations, but we're going to expand them a little bit and specifically talk about neighborhood and zonal operations. Last time I had a little, I think this helps Hattiesburg folks a little bit if I put this on my lapel here. All right. So today we're going to talk about neighborhood and zonal operations. So neighborhood operations are usually, sometimes, I know I've asked this question before, but who's taken a remote sensing course? Right? So they're very similar to what they might call a filter or a kernel operation in remote sensing. You know, it might be a little bit of a review for you. Sometimes there's different reasons that we might do this on GIS data, but they're very commonly used for processing. In fact, you can do these even in Photoshop. Okay? When you do a blur, it's really a neighborhood GIS operation. So if you ever used Photoshop and you went up and blurred a photo, it's basically doing a neighborhood operation. Zonal operations are a way to do, basically to do overlay a little more intuitively than what we talked about last week, where we're just trying to add things together and find out where commonalities exist. So zonal operations are probably the closest one-to-one analogy with. They're kind of like an overlay combined with a summarize. They are an overlay combined with a summary of some sort. We'll talk about those. So remember that these map algebra functions are basically operations that take a map and produce an output. So some of the ones that we're going to discuss today are those. That's actually mine. All right, so these aren't any different, these functions we're going to talk about today, but the way they operate is different, and we'll have to talk about and understand how they operate to understand what they're doing and what applications they can best be used in. So, everything that we've talked about thus far is considered a local operation. In other words, they're performed one location at a time, maybe through multiple rasters, but one location at a time. If you think about it, once the rasters are georeferenced, this type of operation doesn't really have any other spatial component to it, a local operation. In fact, let's say we had a data set that represented a raster data set that represented population in each cell, right? And the population was the population in 2010, and then the population in 2015, let's say. And we wanted to find out what the population change was, how the population had changed. How would we do that? what operation we would do that we've talked about to get the difference. So every cell would have the difference in population. Some would be negative and some would be positive. Most would be positive, though, because usually there's a general upward trend in the population. But how would we get a raster output map that showed us the population difference between 2 years in a raster? Yes. Well, that is where I'm going, though. So in raster GIS, when we do a local operation, we take data set A and subtract it from data set B, and it takes the individual cell values, which are the finest grain item that we have, and subtracts for those data sets, and subtracts the value in data set A from the value in data set B, and the result is a new data set C with the difference. Okay? Now, the point I'm trying to make is that local operations it's basically the same operation that you would do in a vector GIS. Let's say you had a polygon, and that polygon represented a census tract, right? And so you had the population in 2000 and in 2015, right? How would you typically store that in a GIS database? Those would be two different, in an attribute table. They'd be two different fields in an attribute table. And if you wanted to get the answer of how much did the population change, what would you do in that case? Yeah. Right? The first thing you need to do, though, before you even did that, was add a new field and then calculate the difference, right? So, a local operation is an analogous operation in the vector GIS world to a field, creating a new field and doing a field calculation. Right? Okay. Well, zonal is kind of similar to overlay. Focal and neighborhood, it's different. There are ways to do this in vector GIS, but it's not typically done in the same way. And then global is taking into consideration the entire set of values. Some people put global and zonal in the same realm here. So this is a review. I showed this slide last week. Here's adding, but we could do subtracting. All right, so focal or neighborhood operations, it's important to understand how these work. And there's a few common ways that people get confused on how these work. So I'm going to point those out as I do this. But basically, a neighborhood operation works by having a window defined. Sometimes people call it a kernel or a window defined, and they can be of different shapes. When I just ask you, what's a neighborhood in general? What is a neighborhood? Like, don't think about GIS. Yeah, it's a small section of a city that is around, that has some cohesive, attributes, things that make it its own particular region. Well, the only thing that a raster neighborhood has to do with that is that it's a small section of an area. Okay? There's some major differences, though. A neighborhood here is always the same size. So when we tell a GIS to do a neighborhood operation, it's always the same size, and that's defined by a number of cells. So typically, we might see a neighborhood being a 3 by 3 window, or a 5 by 5 window, or a 10 by 10 window, or even sometimes maybe a circle shape. It still needs to be defined, though, by a number of cells. So if it's a circle, then it's an approximate circle. You're either in or you're out of the neighborhood in terms of whether the cell here. So here, the neighborhood is a 3 by 3 window. 3 by 3 window. The other thing about this type of neighborhood is that it always has a focus. And that's where this alternative word focal comes from. So the focus is the cell that receives the output value. So what every neighborhood operation does is for every single cell in the entire raster data set, every cell, I calculate a new value based on the window where that cell that I'm examining is the focus. So right now, this cell is the focus. These are the values in the neighborhood. This is the value that gets assigned to the output raster. So in this case, this is the neighborhood. The function that I'm doing is trying to find the maximum value. And in the output, I'm doing 42 because that is the largest value in the neighborhood. This is the focus, the center. Yeah. Typically, the center is the focus. So this is the output value. This is the input window and the output value. And so what happens is then the computer moves on to the next cell. And the next cell becomes the focus. And I have a new neighborhood. My new neighborhood would actually be these cells and these 3 cells that you can't see. And then, since now this is the focus, it finds the highest value in that square. What's the highest value in that square? We don't know what this value is, or what that value is, or what that value is. But when they made this diagram, they guessed that it was going to be 42, or maybe they actually had the real values. So the highest value in this window right here is 42. And then you would continue on until you filled out all the values in your output raster. So every focal or neighborhood operation has the function that's associated with it, and it has a window size, and it has where the focus occurs in that window. Typically, it's the center. So they move. It actually doesn't matter which way they move. Some people think, well, if I find the maximum in this one, and then I move to here, maybe the maximum moved over. Well, it doesn't even. It only looks at the input data when it's calculating the focus. When it's calculating the window and the focus. So it takes all of these values and assigns whatever function we're looking at. It assigns that value to the center cell in the output. It doesn't change any of the input values. Then it moves over to the next one, calculates the function for all of these cells, and assigns the result of the function to the center cell in the output data set, not in the input data set. So here, this is a neighborhood mean, a focal mean. So here it's a rectangle, it's 3 by 3. So what it's doing is for this neighborhood right here, it's finding the, maybe I'll blow this up a little bit, but it's finding the mean. What's the mean? The average. It's finding the average value so it's adding up 0, 1, 1. Let's see if this works better. Trying to get it so that I can point so the people on Hattiesburg can see too. Okay, so this does work better. 0, 1, 1, 0, 3, 3, 4, 0, 3. So 1 plus 1 plus 3 plus 3 is 8 plus 7. 8 plus 7 is 15, right? Okay, so 15, and then how do we get the average once we've added up all the values? We divide by what? The number of cells, yeah. So we've got 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 cells. So 15 divided by 9 is what? Should be 1.7 if ESRI has produced the right answer. They rounded. Okay. So that's why it's 1.7. Sorry, did you have a question up there in Hattiesburg?
No, we're good.
Okay. All right. So then you move over to the next one, and now it would be these cells right here. 1 plus 1 plus 3 plus 3 plus 2 plus 3 plus 2. It must add up to something pretty close to 15 because you get the same answer. Then you move over to this one. Now the window is like this. This is the focus. And so we get 1 plus 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the sum is 18. Divide that by 9. 2 is the output. So that's how neighborhood functions work. They work by taking everything in a window and performing a mathematical operation on those things in the window and then assigning them to the output grid. And again, it wouldn't matter if we started here and like worked in a circle and got all the way down to the middle, but the computer, it actually is working row by row, so that's why they show it like this. But it would produce the same result no matter where we started and where we ended, because we're only taking the values from this side and attaching them to this side. Okay.
Would you count the square that has no data in it on input? Like, you know how you like count all of them and divide by 9 because that's the average? Would you just not include the no data square, or would the computer not include it, or would it still consider it in the slot?
Yeah, that's a great question. And then also, the edges are basically treated like no data too. So the edges out here, they don't have any data, right? So like when this becomes the focus, see how that says 1? Well, that's because it's the average of 3 and 1 divided by, is it divided by 9? What's it with 3, 4? What's 4 divided by 9? Yeah. So yeah, exactly. So no data is treated as if there's no denominator or numerator value there. So see how this window right here, 3 plus 1 is 4, and there's 4 cells, so we divide it by 4, we get 1. So this no data should be treated the same way. I'm sure different GIS systems handle this slightly different, so it's always good to read the help. But in this case, it's 2, 2, and 2. That's 6 divided by 8. It's what it should be if it's consistent. Let's see. 6 divided by 8 is 0.75, and that's what's rounding to 8. So it is 6 divided by 8. Not 6 divided by 9, because that would be 0.66, that would be 0.7. Okay. So no data is ignored, as if it's not there. So it doesn't add a cell, and it also doesn't add a... and that's how our GIS handles it. I'm not going to guarantee that every GIS system out there, or even remote sensing system out there, is going to use the same technique. In fact, there may be, if you look at the help, there may be a way to get it to treat no data differently. We'll look at that when we actually attempt to execute one of these. So there are lots of different neighborhood functions that are available. All the ones that you might think of, all the statistics that you might think of in your mind. You could get the neighborhood mean, the neighborhood min, the max, the range, and the standard deviation, etc. Can't think of any others that I didn't include, but I'm sure that they're there. You can actually calculate very complex or more complex neighborhoods, and that's actually what slope is. In your introductory class, you should have just like calculated slope once for or maybe more than once for a data set. Did you all do that in intro to GIS class? Did you take a elevation raster and calculate slope? I haven't taught the introductory class here in a little while, but you did? Okay. Yeah, we did it. We calculated it once. We didn't talk about how it was calculated or anything like that, but we calculated it. Well, basically, it's a more complex version of a neighborhood operation. Here's a few more. So slope is a neighborhood operation. And we'll get into a little bit more detail about how slope is calculated. We're going to talk about terrain derivatives for a whole course, for a whole class. Talk about that. Neighborhoods are typically rectangle, but they can be other shapes. Circle is probably the second biggest, the second most common shape for a neighborhood. But you could even do wedges, or what we call an analyst, which is like a donut shape, fancy word for donut shape. And those would be for different purposes. Once we talk a little bit more about what these do, we'll kind of think of some applications. Right? But remember that it can't really be a perfect circle because it's either in or out of the neighborhood. There are some common neighborhood types that you might see when you're reading literature on raster GIS operations. So sometimes they refer to the 4 nearest cells as a von Neumann neighborhood, and as that grows, it becomes like a diamond shape, like this. And then the Moore neighborhood is the default, square-shaped neighborhood. As it grows, it becomes a square. All right. Here, I just included this slide here to re-emphasize the point of that it actually doesn't matter where you start or end, but it's a computer and it is methodically going from left to right like that. Okay, so these are things that are often used in a GIS. How are they used? Well, one of the most common applications of a neighborhood operation is to calculate the slope. The slope is actually really similar to, one way to think of the slope is that we look at the change in this direction change in this direction, and we come up with an average value. So it's like doing 2 neighborhood operations and then a local operation to add the 2 values together and then divide by 2. That's a simple way to put it. We'll show the exact formula later when we get into that class. Now, what do neighborhood functions do? Well, on a simple level, what they're doing is they're actually reducing the variability of your data set because they're taking everything in a neighborhood and condensing that down into a number. Oh, sometimes there are operations that don't look at neighborhoods. They're not commonly used. Another way to think about that is that they're just resampling the data set. But typically in GIS software and literature, we refer to that as a block operation. A block operation are like neighborhood operations, but they are not overlapping. So if we were to take everything, if we were to do a block operation, we take everything within the block and assign the value of a particular function, the maximum, the minimum, to the output raster, and it would have the effect of decreasing the spatial resolution. That's what I mean by resampling. It's one way to resample, to do a block operation. All right, now, the way that I explained doing the neighborhood mean is that I said that we take all the numbers and we divide by 9 because that's the number of cells. Another way to think about that that's the same exact math is that we could take every cell and multiply it by 1/9 and add all those up. So there's a generic operation in most GIS systems that allow you to specify a kernel. And a kernel allows you to take a window and specify a multiplier individually for every single cell. So it's a neighborhood operation, but instead of using a generic mean, I want to find the mean, or I want to find the maximum, the majority, what I want to do is take a neighborhood and I want to apply a function that multiplies every cell by the value in the kernel. So here it's the same moving window, but I'm multiplying each of these cells by 1/9. And in this case, I get the same answer as if it was a focal mean or a neighborhood mean. That's the same thing, it's just the math's done slightly different. Instead of adding them all up and dividing by 9, I just multiply them all by 1/9 and then add them all up. Same operation. It works out to be the same math.
So if let's take that focal point is 12, if you multiply each cell around it by that 0.9?
It's 1/9. 1/9 is yeah.
You would determine each one of those cells by that one around it?
Right. So I multiply this by 1/9, this by 1/9, this by 1/9, and then I add all those values up. I get 11.1, and I would also get 11.1 if I added all these numbers up and then divided by 9. I get the same number. Like I'm using the board here, but 13 divided by 9. I'm just going to do 2 of the numbers. 13 divided by 9 is the same as, well, it's the same as this, though, is what I'm trying to get at. So this is the same math. That's what I'm trying to get at. All right, and imagine that all of the numbers were there. You could pull the 9 out and do the 9 at the end or at the beginning. Now, with neighborhood mean, this doesn't really, you're like, who cares how the computer's doing the math? I understand the math. Maybe you're thinking that. Well, that's fine. But this is the, I'll come back to this slide in a second. But this is the basis behind creating custom kernels that can help us to identify certain things in our data set. For example, we could create a very simple custom kernel where everything inside of this square gets multiplied by this value, and this value in the window. So what it does is it has the effect, what's 0 times anything? Right. Okay. What's 1 times anything? That number. -1 times anything is the inverse of that number. Okay? So another way to think about this is that the output value will get the value on the right minus the value on the left. So that's the number that will be in the output cell. If we do that, operation. So what good is that? Well, it helps us to identify any horizontal edges. So it's an edge detection filter. We can find edges, and the bigger the edge, the bigger this number will be. See how that's an 80 there and a 40 there? And so in our output, this will appear either brighter or darker, depending on our color scheme, than this, and these will appear the very lightest or darkest. So we can see the edges in our data set that run north to south. Yeah, we could identify north to south running mountain ridges. If that was a important data set to whatever feature we're trying, whatever process we're trying to model. Like, let's say we know that it's important to identify north and south running ridges for some process that we're trying to model, then this would be a great way to do it. Or east to west. Sorry, actually this would be east to west ridges. Or no, there would be north to south ridges, right? Yeah. This would be east to west ridges. Running east to west. Horizontally through your thing or vertically through your thing. Through your data set. All right? So those would be a way to discover contrast, differences within the local neighborhood. So what this does is it's going through every cell. So see how when it gets to this cell right here, it would just be 960 minus 960. 960 minus, because 1, these would all be multiplied by 0. 0, 0, 0, 0, 0, 0, 0. This would be multiplied by 1, this would be multiplied by -1, and we would get a number that would be 0 because 960 minus 960 is 0. Whereas when we get down here, when we get to this cell, all of a sudden it's 960 minus 40, and then this one's also 960 minus 40. The cell on the left, the cell on the right. What if we were only concerned about the center cell and the cell on the left? All we have to do is move this -1 over to here, and we get that answer. So you can put the values wherever you want. If you're interested in more diagonal trends, you could do these. What if we're interested in either diagonal trends or, east-west trends or north-south trends? Well, we could calculate both of them and then add these two resulting data sets together. And then we would have the total change in both directions. So we would have the two different types of change. If we were just concerned about variability in all directions, we might do something like find the standard deviation, the focal standard deviation. So it would tell us about all the variability that existed in that window.
So, Doctor, we would have to calculate the horizontal, and then you couldn't calculate it simultaneously. Because that would be my first week to try and calculate it together.
Well, if you did it together, then you'd be looking at the difference. You would still get an answer. Like if you made this 1 and this -1, then what you would be doing is saying, okay, take this one and this one, and subtract it from this one and subtract it from that one.
So it wouldn't give you like the right, or would it?
Well, let's try it. So, yeah, this one right here is where. So right here, it would be different. So we take 980 plus 940, which would be 18, 19, 20, I think, 19, 20, and then it would take 940 and 900, which would be 1840. I said 1920. Okay, so 1920 minus 1840 is what? Yeah, 1840. 1920 minus 1840. 80. So all of a sudden, 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. So it'd be that one. Yeah, it'd be that one would become 80. And it looks like that would work.
Okay.
That would be the same math.
I just didn't know if you ran them together, if it would. So I guess you just have to be aware of what's going where.
Yeah. So if you want to do the sum, that would work out. If you wanted to do the average, I guess what we'd have to do is turn these to negative 0.5 and positive 5 to get the average of the two data sets. If we're only considering two values. All right. So go back to this slide here, though. Once you start talking about kernels, you can't just ignore no data, because what happens when the kernel gets to a corner? like I said, different GIS systems probably handle things a little bit different, but some will automatically, if you specified each one of these is 1/9, it might take the corners and change them to 1/4 and the margins to 1/6 for you. It might do that math for you. Okay. Another thing that I've seen GIS systems do is just throw away the corners. If the whole window isn't covered by data, then in the output data set, it becomes no data. Okay, so basically, every time you run a neighborhood operation, your map becomes slightly smaller. So I've seen that happen in other GIS systems. I'm pretty sure ArcGIS does this for you. It recalculates the values that you're giving it at the corners. But in any case, you should either figure out what it's doing or make your study area large enough that the very corners aren't of great concern. Because if you don't know what it's doing, it could be producing results that aren't effective. Okay, so here are some reasons why you might, I've already said, you might do it to identify edges in your data. Doing what we call a neighborhood mean, it smooths your data out. So what you want to do, the reason that you might want to do that is it will take anomalies out of your data. So if you have something that is in your data that's kind of noisy, like let's say you have an elevation data set and there's some noise to it, and you don't know how that noise got created. It's an artifact of the processing that went into creating that elevation data set. One thing you might want to do is smooth it out. And you can smooth it out by doing a neighborhood mean. Sometimes we refer to neighborhood means, particularly in remote sensing, refer to it as a low-pass filter, but it means the same thing. Sometimes, so we might want to do that because of noise. Sometimes we don't want to do it. We're going to do it in today's lab. We might want to do it to fill voids. Let's say we have a raster, like if we go back to this right here, we have a raster, and we know that there should be an elevation data set right there. What's the best guess for the elevation right there? I mean, what are some of your ideas? If I wanted to, yeah, it's probably close to somewhere around it, particularly if it's temperature, right? If it's elevation, there could be like a big spike there. It's possible. But it's still a good bet that, because of Tolber's first law of geography says that values that are nearby tend to be similar. So yeah, but if it's temperature or precipitation from like a rainstorm, values change pretty slowly over the landscape. So if we wanted to make sure there was a value there for our analysis, we could calculate the value. We could say we could run a neighborhood mean and find the average value and replace that value there, that no data value, with the result of the neighborhood mean. So in other words, that value, if we did that here, that value would become 0.8. That's acceptable. What if we determined that we should just use the minimum value within the window? That might be better. Or the majority, the most often repeated value. That might be an acceptable one to use as well. In that case, that number would become 0, the majority, because we got 1, 2, 3, 4, 5 zeros in that window, and we've only got 3 2s. So if we do the neighborhood majority, that would be 2. Now notice that now I am talking about putting these values back into this grid, but that involves a different step. So step 1 would be to create this data set, and step 2 would be to take this data set and put it back into this data set where no data sets occurred. So mathematically, what I'm talking about is saying create the neighborhood mean, and then take that data set and say, if this value is null, take the value out of this data set, and if that value is not null, leave it the same. That's actually the exact process that we'll use today in the lab to fill some voids. All right. Another operation that's oftentimes done is to accentuate the differences between cells. If we want to see where there are big differences in the data, we can do the opposite. Sometimes we refer to it as the opposite. But a high-pass filter, it accentuates the difference in the moving window. So what it does is the focus gets multiplied by 9, and all of the neighborhood, the rest of the neighborhood gets multiplied by -1. When we add up all those numbers, then if the center got multiplied by 9, it gets a lot bigger, and then we subtract all the neighboring values, and they get smaller. So the bigger the difference, now the larger the overall value in the center. So when we do have things that are significantly different, they wind up even more different than their neighbors. So that's the output. So they increase the spikes. They basically increase they increase themselves relative to their neighbors, doing a high pass filter. We could play with these a little bit, these numbers a little bit, if we wanted to accentuate it even more. But they work out nicely because what you're doing is you're multiplying the center value by 9, and then you're subtracting every other value off. And so if they were equal values, you're going to get a number close to 0. In fact, if they were exact, if all the values in the window were equal, you would get a value of 0. So that's why when you get a very high value, it means that it was a lot different than its neighbors, relative to its neighbors. All right. And then the next step might be to say, well, those values were probably, those really high values, we could set a threshold. We could say, those really high values were the result of a mistake. If this, like, let's say this represented an elevation data set. Well, I've seen data sets where there's mistakes in them, or even images. Like, let's say we have an image of from satellite imagery. We have some really bright or really dark pixels. We could use this to identify, set a threshold, and then we could do another conditional operation where we say, if it is a value that's well above what it should be, replace it with the mean value, or replace it with the maximum value, or the minimum value within that window. So that's a way of removing spikes and pits by high-pass filtering. I already kind of mentioned this is another reason for doing moving windows, and that is to look at the spatial covariance. The more related they are, then, when you do a moving window operation, your values in the moving window become more related to each other. So you're increasing the spatial autocorrelation of your data set when you run a moving window, a focal neighborhood operation. I know I'm using lots of terms, but there are several terms that are used. If you did some of the reading, you'll notice that different authors refer to them differently. ArcGIS, we'll see in a second, but sometimes they call them focal, and sometimes they call them neighborhood. So that's why I use those two terms the most. All right. Before we shift gears and start talking about zonal, let's just talk about this inside of ArcGIS. Yeah, let's do the new data set. I'm going to shut this down. This is last week's, and open up ArcGIS Pro, and I'll just start the lab up. I'm not going to. It's interesting that I get that error. Okay, so I'm going to import the lab data. I'm going to call this SA3 or EX3. I'm going to import some of the lab data into this data set. So I put it under ctemp. One thing that I'm going to do is I'm going to connect to that folder that I downloaded on my computer, ctemp, so that I don't have to keep finding it. Ctemp. SA3. Is that where, that's where I put it. But did I unzip it to there? I gotta unzip it. It's gonna go like this. Copy and put it right here. So now I've got that all in. So this lab is based on some actual analysis that we did. So I have a few data sets in here. This one that's called Big Pine Key is the same as the elevation data set, except for I think it's smaller. It should be smaller. That's what I wanted to do. I don't think it is smaller. Nope. It's also, I also converted it to be meters, the elevation data set. So this is the one we're actually going to use for the lab, the elevation.img data set. I'm just going to delete Big Pine Key because that one was the original data set. The elevation data set, though, is the one we're going to use for the lab. So yeah, elevation data set is smaller. I meant to make one that was even smaller. So if I zoom way in here, you could see that we've got some elevation data where the bright areas represent higher elevations. So the elevations range from -2 to 12. Anybody ever been to the Florida Keys? Okay, but you can imagine there's not a whole lot of mountains there in the Florida Keys, right? Like 12 meters above sea level is probably actually a pretty high hill on a small island. See how small these islands are? This is zoomed out, you can't even see them. So this key right here is called Big Pine Key. All right, so what we're going to do with this elevation data set is practice doing some neighborhood operations. Okay. So if I go to geoprocessing, I'm going to go to the toolbox so we can see where these are. I oftentimes just type them when I use them. All right. So you can see that there's a toolbox called neighborhood. And the neighborhood toolbox allows you to do a lot of these neighborhood operations that we've been talking about. There is the block statistics tool, which we're not really going to practice today or go over. But remember, the blocks are a little bit different than the moving windows we talked about before. They're non-overlapping. It's less common. People still do it. All right, we're gonna practice using the focal statistics tool. That's really the tool that you use most often in this toolbox. So the focal statistics, what it does is it calculates for an input raster. It calculates an operation for a specific focus. So I've got my elevation data set. I'm going to put it in there. And then this will be my output data set, which is fine. It's just going to store it by default in the file geodatabase I'm working in. And here's where I can specify the rectangle, how big I want the rectangle. By default, it's a 3 by 3 rectangle. I think what I'm going to do in order to actually be able to really see the differences is increase this just for the first time I run it to a 7x7 rectangle. And I'm still going to choose the mean as the output. In fact, I'm going to change this to focal mean 7, 7, just so that I can keep track of what's in the data set. And then I'm going to hit run. It's going to take a few minutes probably to run. No, not a few minutes, but more than a few seconds to complete that task. Because you can imagine how, you can't even see the individual cells here, but you can imagine how it's going out to every cell value. Okay. Now look at, what would you say changed? Did the maximum value change? No, I'm a little surprised it didn't. But what did change between these two data sets? Let's zoom in a little bit, be able to see this a little bit better. Okay. What would you call that effect? Maybe you'll zoom in a lot more. You think it enhanced it? Yeah, it definitely made it more blurry. Okay, it took the original data and it smoothed it out. That's what the mean filter does. It smooths the data out. Okay, now what did it do in the no data areas? See how this was a no data area. Now all of a sudden there's data in there, right? So it didn't do it exactly the way that the slide did it. It took a 7x7 window. So there's a cell right here. We don't see it, but there is a cell right here. We could make it so we do see it by changing the symbology. So we're going to make no data orange. So there is a cell there, right there. Its value is no data. If we run it on this elevation data set, the result, the focal mean, is now at that point 2.33. So within a 7x7 window, it's replaced that value out from no data to 7.7. So it took all of the values within 7x7 window and calculated what value it was and assigned that to the output. So over here, there's no data. I wonder what would happen if we come back in here and uncheck ignore no data in calculations and then call this something slightly different and rerun it. So that's the output now. Notice that it did not eat away at the no data values. And kind of what's kind of even more interesting is that it actually took, there's actually more no data values. So anything that was in this area, anything that in the neighborhood of a 7x7 area that was no data became no data in the output grid. So you've got those two different options. For this lab, we're actually going to use this one, this ignore no data in the calculations, that basically eats into the no data. Because we want to get into the no data, because what we're trying to do is remove some of these data voids. This is a data void, that's a data void. We want to remove the data voids. All right. Filter is the way that you can do a low pass filter, which is basically a neighborhood mean, or you can do a high pass filter. So if we want to take our original elevation data set and find spikes or pits in the data, we can do that using the high pass filter. I'm going to run this guy, and we should have accentuated the changes instead of reducing the changes. So now anything that's very bright or very dark are big changes, and all of the stuff in the middle means there's not a lot of big changes. So we see a lot of kind of boring map with some changes. So we can see more variability over here. More variability occurs, I guess, right around the bodies of water. Now, there's there we go. So, if we want to do what I talked about before and create a kernel in ArcGIS, the way that that's implemented is to actually choose weight. If you choose the weight option down here, then you'll have to specify a kernel file. And we can go read the help about that. We're actually going to do this in a couple weeks when we talk about slope. But I'll just bring this up here real quick. So we're not going to do this in today's lab. But if we want to create a kernel, this is how we do it. I'm just trying to get the help. So, so how focal statistics works. And I'm just trying to get the format for the file. Yeah. So this is how your file has to look. There we go. This is how your file has to look. It has to specify how many rows and columns there are, and then it has to specify the weight in each of the cells for your neighborhood. It then takes this neighborhood and goes around and calculates the value for each of those cells, and then adds them all up. So it'll multiply this one by 1, this one by 1, this one by 1, this one by 0, this one by 0. So this is basically just summing up only these cells in a window. It's not a very interesting kernel. See if they've got another example. Oh yeah, there's another example where we're basically taking a 3 by 3 area and we're multiplying only these 4 cells by 0.25, negative 0.25, and this one by 2. What does that one look the most like that we've talked about today? It's similar to the mean filter, but the mean filter, they would all be negative 0.25, or they would actually probably all be negative 0. They'd all be 0.2. So if this was 0.2, 0.2, 0.2, 0.2, 0.2, that'd be the same as 1 over 5, right? Because 1 over 5 is 0.02. I mean 0.2. All right, that would be a mean filter. This is actually the high pass filter. It's taking all of the neighboring cells and it's weighting them equally so that they add up to the center cell. So this is being multiplied by 2, which if you add it up 0.25, 0.25, 0.25, and 0.25, you get, you just get 1. But it's similar to the high pass filter. It's doing a similar thing. It's weighting the center cell positively and the neighboring cells negatively in order to accentuate those changes. Right, so that's how you implement a kernel, is you choose weight. And then you have to actually load up a file. How do you make that file? Well, let's just do this. Actually, I'll do this real quick. So you can make it in Notepad. Oh, I just opened up Notepad++. I don't know if that's on those computers, so I'm just going to open up regular old Notepad because that's on every computer. So if I said 3.3, and then I'm going to do the one that we did, that we talked about that looked like this. Remember, what did this filter do? What's that filter going to do? Yeah, it's going to detect edges that are running north-south in our data. So I'm going to save this. I'll just call it oops. I didn't know you could save a file as just .txt. ns.txt. And then I'll just minimize it. So I'm going to run this on the elevation data set, and I'm going to choose wait and then choose that file. Put it on the desktop. Mean, that's right. No, statistics type. Actually, I don't think that this has anything to do with, yeah, well, this is going to cause it to add up all the values after it does. So that's right. I think I should actually choose sum, but this will have the same effect. So that's the output. And so I should be able to zoom in and notice how, particularly this, see how much stronger this north-south edge looks than, let's look at the original data. So here's a pretty strong east-west road right here. Right, there's another east-west road. If I turn this off, I can barely see it. Those appear very smooth, but there's an embossed edge around this north-south road. So these east-west ridges are smooth, and the north-south ridges are more accentuated. Yeah, that's the one I just created. So I put in this. Yeah, that'll be the weight. In fact, if I could save, I could do this again. Change this to 1, this to -1, this to 0, and we could just like kind of look at the comparison of what it would do. File. I'm going to save this as EW, and then choose EW. And then I'm going to leave this mean. By choosing mean, it's going to add them all up and divide them by 2. So I'm going to get a different value than if I chose. I should probably choose sum, but anyway, I'm choosing mean. But I want to keep them consistent. So if we look at the distance between these two data sets, the difference, I mean, see how this data set accentuated all the north-south changes, and this data set accentuated the east-west. So now we see the east-west roads are embossed, and the north-south roads just look smooth. Whereas this is the north-south edges are embossed, the east-west roads look smooth. And obviously, if there's more vegetation growing by the side of the road, you're going to get a stronger. So if we look at the original data set here, the original data set, you see how this road is so much lower than the surrounding area? That's why on the north-south edges, it appears a lot stronger than this north-south road. On that north-south road, there's not a whole lot of difference between the neighboring areas. Actually, right here, there's a pretty big difference. Those are some tall buildings right around the canal. So these are like probably boathouses. You can see those, sorry, in the north-south one, you can see those edges embossed really well. Those areas between the buildings. The orangish, I think what you're seeing is brown, is no data, but yes, it's water. This data set was collected using a LiDAR instrument, and LiDAR instrument, depending on the wavelength, most topographic LiDARs don't penetrate the water at all. They don't go into the water. So, all All right. So that's demonstrating the different types of filters. We could do let's go back to rectangle. We could do a standard deviation, because this will give us some idea of the texture that's present. I'm going to do a little bit bigger area. I'll do 7 by 7 here. Usually you choose an odd number, because if you don't choose an odd number, there's no telling where ESRI is going to put the focus. So if you choose an odd number, 7 by 7, the focus is going to be the fourth cell and the fourth cell, because that way there's 3 cells on either side. I should have, I renamed my other filter, sorry. So this just got named out. Okay, so standard deviation is really interesting. See that? Output. It's called east-west edges because I overwrote the other one. But now what you see is in bright areas, there's lots of variability in the elevation layer. So this might be useful in cases where you're actually trying to detect texture. So sometimes when people are modeling the flow of water over the earth, they say, well, water can go faster if the slope is higher and there's not a lot of vegetation that's causing differences in elevation values. So the texture of the earth is smoother, water can go faster. The texture of the earth is more coarse, the water flows more slowly, plus elevation. Let's just say we're trying to model it. It's a simplification of reality. Okay? Well, if we did that, then what we're trying to do here is we've created a layer that shows the areas that have a rougher texture. There's more difference. We can say rougher texture, but there's more variability in the window in terms of the elevation value. So one way to say that is that there's a greater surface roughness. That's one way we could model. If we're trying to quantify surface roughness, that's when we can model it. Watch if we, in this case, if we make this a 7 circle, it might look a little bit better. See how when we zoom in here, we get these artifacts? Looks kind of like a square. So now I'm going to run this again. So this is still standard deviation. A standard deviation, for those of you who may not have taken a statistics class, you could think of it almost as the average distance from the mean value. So you might want to do a circle because it might create a more visually pleasing shape. So the higher values mean that there's more values that are different than the mean, so there's more variability there. Sometimes people just use the range for that same thing because it gives you the difference between the minimum and the maximum value. This is going to look similar. But now instead of being the average distance from the mean, it's just the absolute difference between the minimum and the maximum value in a window. All right, so those are different filter types. So we're going to shift gears here and talk about a different concept, and that is a zonal operation. So zonal operation is one of the most important analysis tools in ArcGIS, I believe. And anytime you want to ask how many raster things are inside of a certain area, that's the kind of general form of the question for a zonal operation. The way a zonal operation works is that you have 2 inputs. You always have 2 inputs. So you have a grid that represents the value that you're trying to summarize, and you have a grid that represents the zones that you're trying to summarize on. Okay? So all sorts of reasons that you might want to do this. So let's say you have a data set and you're interested in finding the average elevation in a certain city, you're going to use a zonal operation. Because your city is going to be the zone, the elevation data set is going to be the data set that you're operating on, and your output is going to be a number for every single zone that you have, which will be the average elevation. So one of the most commonly used zonal tools is going to be either the tabulate areas or the zonal statistics as table. This is really a commonly used tool. And this doesn't output a new raster data set. It outputs a table where you have one column that has all of your zones, another column, or maybe multiple columns that represent the average elevation or the average precipitation, the average raster value in each of those zones. So here is a walkthrough on doing that. Okay, so if we have our zone grid, these represent zones. They don't represent values. So this could be represent land cover, let's say, or cities. It probably doesn't represent cities. Well, some cities do actually have non-contiguous boundaries, but it's less common. But let's say this represents land cover. And let's say this grid represents the land cover, and this represents, I keep using elevation, so I was trying to think of something else, but let's just say elevation for now. What's that? Okay, it might represent the, like an NDVI value, a vegetation value, the amount of vegetation in that cell. Okay? So here, when we do a zonal max, we're saying in grids, everywhere where this is 1, we want to find the maximum value in this set of grid, in this grid, in the other grid. So what's the maximum value for all of the 1s in this cell? So imagine if we could, I guess if we have the new system that we're supposed to have up in Hattiesburg, I could actually draw. But imagine if we, maybe you can draw on this guy. Hold on. Take notes on this one. No. What I'm trying to say is this has a value of, these 1, 2, 3, 4, 5 cells have a value of 1 in the zone grid. And so the zonal max says, what's the maximum value out of 0, 1, 3, 1, and 0? Well, the maximum value in those is 3. So all of the values that were 1 become the zonal max, which is 3. Okay. All of the values that were zeros in this cell, 0, 0, 0, 1, 0, 1, 2. So all the values that were 0 here become the maximum value, which was 2. And then you continue on. 2, 2, 2. There's 3 2s here, and they all become 2 because of these 3 values, 1, 2, and 2. 2 was the highest value. Okay. Now, this type of pure zonal operation is probably less commonly done than what I described before, where it actually creates a table. But there could be a reason to do this. So for example, let's say you wanted to find out how different every cell in a zone was from all of the other values in the zone. So you could find the mean zone value, and then your output would be the zonal mean. Then you can subtract the zonal mean from this data set, and what you would get is the difference from the mean within the zone. Not the mean of the overall data set, but just the mean within the zone. So what that would tell you is something like, okay, what's the most unusual elevation or vegetation data point within an entire city or within an entire land cover type. So let's say I had a bunch of forests. Okay, and there were different types of forests, and I wanted to find the most unusual elevation value for each forest type. So I could first calculate the average value for each forest type, and then take the average value for each forest type, which would be the output here. So I'd do a zonal operation to do that. Then I'd do a local operation to take that value and subtract it back from the input value, and the final result would be every grid cell would be the difference from the typical the typical elevation value.
So you would subtract that, the input grid from the output, that final zonal output.
I would take the zonal output grid and subtract it from the original elevation data set.
And that would make what?
It would give you the difference from the average for each zone, instead of giving you the difference from the average of the whole data set. So you could then say, okay, well, which one has the highest value in each zone? And you could explore those regions. Why is this elevation in this forest type so different? You know, what's causing that process to occur? Because typically elevation is, especially higher elevations, are correlated with what types of plants can grow in certain areas. You get high enough and trees can't even grow, right? Come down a little bit, you're only getting pines. Okay, you come down a little bit further and you can get mixed hardwoods. So if you wanted to identify areas, the highest areas that hardwoods had occurred, then you could do a process like I had just said. But it would be more like you're also trying to find the highest areas that hardwoods had occurred and the highest areas that pines had gotten to, and the highest areas of any other forest type that you'd had.
And you only want to plant those areas that are giving you optimal output for that particular species you plant.
Yeah, that might be the end goal. All right, so the zonal tools either produce an output raster or a statistics table. They produce one or the other, depending on the tool that you choose to run. We'll show that in a second. Okay, what it does is it creates an output that summarizes all of the values within a zone. It's always summarizing it, just like the neighborhood operations. You have to have an operation that you're doing. Okay? So for every zonal operation, you tell it which zonal operation you're doing. Are you trying to find the average value within the zones, the mean value within, mean and the average are the same, the maximum value within every zone, the minimum value within every zone, the standard deviation within each zone. What are you trying to find? Then you need to specify your two input data sets. And your two input data sets are always a zone data set and a value raster. That ArcGIS actually refers to it as a value raster, as do a lot of other literature data sets. So here's some examples: a developed area map, an erosion potential map, a land suitability map. We could go back to our lab last week. Let's say we had a bunch of potential areas that we wanted to put parks. Okay? Maybe I should have extended last week's lab instead of rewritten the other lab. We have a bunch of areas of potential. We could come up with the average suitability for every potential park. The parks would be the zones, and then the output of our suitability layer would be the value raster, and we could calculate a number that said what's the average suitability, or maybe the total suitability of each park. Average would probably be better because the parks might vary slightly by size. Yeah, you'd have to define the parks. Right. But yeah, thinking back, I actually did this in my undergraduate class. We were we were actually doing like a brand new city park. Okay, so we had to identify all the we actually had to drive up and find empty lots and mark them to the city. So if we had a bunch of empty lots and those were the only locations for cities, and we also had a suitability map, we could overlay those two using a zonal operation, and then we could color code each of the potential parks by their suitability and show that on a map. Okay, so typically you're going to run tabulated areas or zonal statistics as table. This is probably the most common one, but there are other zonal tools. Like I said, you can actually create a new raster. But if you output either of these two, you get a statistics table. If you output the other zonal tools, you'll end up with an output raster layer. I can demo both of those. So you can, like, let's say your zone layer can actually be a vector data set. It doesn't have to be a raster data set. So it can be polygons. And even if it isn't polygons, it probably has an attribute table. Because remember, when does a raster data set have an attribute table? We talked about that the first week we met. For example, remember when we pulled up the Laguna Beach data and land cover? It had an attribute table associated with it, right? What was special about that land cover data set? Was it a floating point data set or was it an integer data set? Integer data set. ArcGIS will automatically create a raster attribute table for your data if there are less than a certain number of unique values. So that's, and it has to be an integer data set. So any integer data set with less than a certain number of unique values will have a raster attribute table. So anyway, something like land cover will have a raster attribute table. And then you could join this statistics table back to the original data, and then you could symbolize on it. What I mean, I'll just demonstrate that real quick. So I'm going to open up ArcGIS Pro again, but do the but bring up last week's lab.
You recording all this, right?
I am. Yep. 3. Yeah. Okay. Let's see. We've been meeting for about 2 hours. Yeah. Why don't we take a 10-minute break? I'll bring up the data, and then we'll come back at 3:10, and then I'll show what I'm talking about here.
I had to like meet like or I had to like meet like page links. So I think I just need to
What's your master's gonna be in?
Geography.
Yeah.
But I'm focusing more on urban design and planning and sustainability with urban systems and things like that. So,
Sis job, yeah.
so that's what I'm focusing on right now. That's what I think I'm gonna write my thesis on, is urban stuff.
You already think about it.
I've been researching it now. I'm with doing an independent study with Dr. Holt, so he's helping me start the writing process. And so he's about to pretty much just like searching and stuff like that, like getting together my lit review and things like that, so I can start writing.
and in turn like the highest value would be like
What,
0.
how big does that be?
And then the lowest value would be whatever.
It'll probably be a few hundred pages by the time I'm done with it, or at least 100 pages. But what I'm doing this semester is I'm writing a proposal, pretty much, and I'll probably try to make that 10 pages. Like 20 maybe.
Yeah.
Depending on how long my lit review has to be, or is going to end up being. It's easy to get a big giant lit review. So, we'll see. Probably 200 is what I'm imagining by the time I'm done.
Hey, you know,
I mean, I knew that because I think
Go up on your map.
he didn't show me that. He should have.
You can go
Like I should have.
on it, but your PhD dissertation has to be an original idea, like an original problem that you're solving. You can't do anything off of somebody else, you know.
My daughter,
Especially in the model. I
my daughter did.
mean, I guess
Told me
told me
not to worry. Because I'm more prepared.
Well, and to be fair, it didn't say like 5 class time. And it didn't say, it just said today.
Like, I mean, I turned in on time and everything, but now I'm stuck doing something I'm not really interested in, so it's not, you know what I mean?
What did you think?
The environmental racism about how, like, landfills and power plants.
Environmental justice.
Yeah.
I was telling him how Jody where she went to a false sense of security.
It's like something I know the answer to, so I'm just basically.
I'm always waiting for it.
It's always around places where people have low income or, yeah, exactly. Or small minority ethnic
Not
groups.
in my neck, not in my neck. You got to do my New York.
Sun's out now.